Okay, I think we'll get started. So this is the third lecture in the mini-series on the Gibbs Phase Rule. And the first two, now we've set out the phase rule, and now we want to see it in certain settings. And again, we would get into the real thermodynamics to calculate some more of the details, but when it comes to sort of an overview picture, it's always nice to fall back on the Gibbs Phase Rule. So I'll remind you that the Gibbs Phase Rule is just the number of degrees of freedom for the system is given to us by the number of components, and we know about the subtlety of the components now. Not just the species, but the species minus any kind of reaction equations that are there, or chemical reactions. Plus 2, that's the temperature and pressure, typically. So these are the two thermodynamic variables. These are coming from the concentration independent variables. And then minus the phase, number of phases. So we'll talk about phase diagrams, and we go through this a little bit in general chemistry. So if you've had some general chemistry, you've talked about this, and then comes back again in physical chemistry. So just to give kind of a reminder, I'll go through how we look at this phase diagram, what it tells us, and then we'll get into looking at some examples of the Gibbs phase rule there. So we plot pressure and temperature, and then we plot lines in which the chemical potentials are equal. So that will represent lines of equilibrium. So if we look at something that is at low temperature and high pressure, we would expect that to be a solid. If we're at low pressure and high temperature, we expect that to be a gas. And then somewhere intermediate to those extremes, we expect to have a liquid. We have a solid gas equilibrium that rises from zero pressure, absolute zero temperature, up to this point here where we have a bifurcation into a solid liquid and a gas liquid curves here representing the equilibrium. The conditions for equilibria are that the chemical potentials are equal. So here we have chemical potential of the solid equals chemical potential of the gas. Here the gas and liquid are equal, and here solid and liquid are equal. The solid line continues off to infinity, so there is no way to go from a solid to a gas or a liquid without a phase transition. Conversely, the gas-liquid line terminates at what's called the critical point. So this is the critical point. Anything above that point on this graph, so up in this area here, is called supercritical. And notice you can get from a liquid to a gas or a gas to liquid by going around the critical point and never undergoing a phase transition. All right. The types of transitions that happen here are called sublimation if we go this way, and deposition if we go that way. Here we're called melting, here we're called freezing, and here we're called boiling and condensing if we come back the other way. All right, so that's a general phase diagram. This is typical for different solutions, or different species. There's some variability, of course, certainly variability in the actual values of those, but this is a pretty typical phase diagram that you're likely familiar with. Okay, so let's look at some special points on this phase diagram and apply the phase rule, and just let's think about what the phase rule is telling us. So let's look at state A. So here we're off in this, actually, I think, give myself some room here. We're off in this area, and I think I'm going to work with a black marker here. We've got a single phase, gas phase, and we have one component. So we're always going to have one component here. We're talking about a single component system. So our phase rule says 1 plus 2 minus the one phase equals 2 independent variables. Now you're always free to choose what variables you want here, but a very typical or a very convenient one would be this system. Put a little coordinate system on that dot, then we have pressure, temperature. So these two variables can most conveniently be interpreted as temperature and pressure there. So we're free to fiddle with the temperature or the pressure, and we still maintain this same phase. We don't change the situation. we're still a gas in this case. Okay, well, let's look at state B here. Now, B is on the lines, specifically on the line. So we think there might be something different here. We're in equilibria between two phases. So we have now phases equal 2, components still equal 1. So we have 1 plus 2 minus 2 equals 1. And so you might be tempted to say, well, what is that 1? Is it pressure? Is it temperature? Well, it's really neither, because let's look at what happens if we make a little change in pressure. We go off of that curve. We're just into a single solid phase here. Or if we go a little bit in temperature here, then we're just in a single gas phase. So we do indeed have 1 degree of freedom, but it's a combination, a so-called linear combination of the temperature and pressure. So we can think of some variable, say y, or let's call it z, is some function of temperature and pressure, right? And we'll make this the independent variable and say we can twiddle z a little bit, and that will run us along that line. Okay? So now let's look at, see, this is called the triple point because 3 phases are in equilibrium, solid, liquid, and gas. So we have 3 phases here, 1 component, and so we have 1 plus 2 minus 3 equals 0, and thus we have no degrees of freedom here. And if we look at this, there's nothing we can do to maintain that point. If we move in any direction there, we cannot maintain the system. So unlike B, where we could move along this line and we're still in this gas-solid equilibria, the triple point, if we move away from the triple point, we're no longer in equilibrium. Okay, let's look at D here. Now D is kind of neat. It behaves just like B, but let's look at that. It'll make a connection a bit to our condensed version of the phase rule, which we talked about in the first lecture. So phases 2 again, because we're solid and liquid, and then number of components 1, of course. So we have 1 degree of freedom. Okay. Now, for a typical phase diagram, this is almost vertical. Now, importantly, it isn't, and there is a slight curve to that. It can be either leaning this way or this way. Most often, it leans this way. Slight curve, slope this way, and then or a slight slope this way. And that does matter physically, but it is by and large nearly pressure independent. So if we move up and down in this direction, this z variable we had before over here really corresponds to pressure. Because if we change, it's very sensitive to temperature, this equilibrium. So we go just a little bit in either direction, we are out of this equilibrium. But in the p direction, we're not. So we can nearly think of p as the system being independent of p, unless we have very large pressure changes. So that is the basis for the condensed. Well, I shouldn't say that's the basis, but that's where we see the condensed version coming in most clearly here. So if we look at the condensed version, we're just eliminating pressure. So we're saying pressure, let's not count pressure. In which case we would get 1 plus 1 minus 2, or 0. And that really does show here that if we were to change our temperature variable in any way, we would move off of that equilibrium. So it is fixed in the condensed version. So although the condensed version isn't the formal Gibbs phase rule, it does have some application. Okay, now let's look at state E. We're up here in this supercritical region. Supercritical is it's really neither a liquid nor a gas, kind of characteristics of both, but it is a single phase. So it's 1 phase, 1 component, so we have, just like any point, just our generic point here, A, we have 2 degrees of freedom. And again, the most natural ones here would be temperature and pressure. All right, let's look at state F. Now, a little bit of a subtlety here. We might think there's 2 phases, liquid, gas, in which case we would go 1 plus 2 minus 2 equals 1. And that would be very much the analogous to the case we had down here, where we could traverse along this curve as a 1 degree of freedom. But notice we are at the very edge of this. So we could come back this way, but we can't go that way. So the limiting, or the terminus of this line, we really have to consider 3 phases here. The liquid, so one way to think about it would be the liquid, the gas, and then the supercritical fluid as being a separate phase, even though there isn't a phase transition happening to go there. So technically we really should have this. Now, what does this mean? How do we interpret this? If we go off this way, we become supercritical. There is no liquid-gas equilibria. Two phases there. If we go this way, there still is 2 phases, but we are now no longer at the critical point. We aren't just adjacent to that point where the system goes supercritical. So the better way to think about the Gibbs phase law here, in this where the line terminates, is to consider this this green version here. All right, so that is the phase diagrams, and so we see here how the Gibbs phase rule kind of flavors the discussion of the phase diagrams.